All right, well, I have the, I guess, pleasure of starting the last session of the conference. I'm Tim Middleton. I'm a principal consultant with HMMH. We are an environmental consulting firm, and I focus on aircraft noise. And the last session is new entrants. And so new entrants is a very relevant topic for this symposium as we look to the future of where the aviation industry is going and the new aircraft and vehicle types. As you recall from the FAA's NPR, they're referring to them, these new entrants, as vehicles, because some of them are not traditional aviation type aircraft. So with that, we're going to talk about supersonics, electric aircraft, and eVTOLs. And I'm going to introduce our first speaker, Dr. Nathan Cruz. Dr. Nathan Cruz joined NASA Langley Research Center in 2021. His work at NASA focuses on supporting the planning and execution of community noise test campaigns during the Quest mission. Prior to joining NASA, he served as a research mathematical statistician at USDA's National Agricultural Statistics Service for more than 8 years, where his research focused on improving crop and economic estimates by combining survey and auxiliary data through statistical models. He holds bachelor's degrees in economics and mathematics, master's degrees in economics and statistics, and a PhD in interdisciplinary programs, all from Ohio State University. Dr. Cruz co-chairs the Federal Committee on Statistical Methodology Interest Group in Computational Statistics and the Production of Official Statistics. So, Dr. Nathan Cruz.
Thank you all, and thank you for the chance to be at this wonderful conference. I'm going to share an overview of some of NASA's intentions with the X-59 aircraft, culminating in community testing. And Sandra, if you will, would you go ahead and launch the animation on this slide? And so our focus is on quieting the sonic boom. And so what you see in this animation is that the sonic boom happens when shock waves form on any object that's traveling faster than the speed of sound. From the perspective of a listener on the ground, it's a loud and perhaps startling impulse noise, kind of like an explosion or a thunderclap. But crucially, the sonic boom travels with the aircraft for as long as it's in supersonic flight. So you can imagine this large carpet, if you will, spanning from New York to LA if supersonic flight is happening over land. In part, because of this phenomenon, supersonic flight over land is prohibited. And so that's codified in the Part 817 here. It's really a speed limit imposed on any civil aviation, civil aircraft, and prevents people from operating at speeds in excess of Mach 1 without specific clearances from the FAA or without assurances that the sonic boom doesn't reach land. And so what that means is that any prospective commercial supersonic transport could really serve overseas routes as opposed to routes over land. Much has happened, though, since the enactment in 1973. And so there are prospects of design that can quiet the sonic boom. And so this is really what NASA's Quest mission is designed to do. We're going to fly the X-59 aircraft, gather community response data, and provide that to noise regulators to decide whether the speed limit should be replaced with a noise limit, and if so, at what levels. In brief, the NASA Quest mission has 3 phases. Phase 1 is about building and flying the X-59 aircraft. This is a one-of-a-kind demonstrator aircraft. The contract to build it was awarded to Lockheed Martin, and we actually expect the first flight of the X-59 later this year in 2023. Phase 1 is about building the aircraft and proving its flight worthiness to operate within the national airspace system. Subsequently, in Phase 2, to be conducted starting in 2024, we're going to spend some time validating the acoustic tools that we are developing to measure a one-of-a-kind phenomenon, the quiet sonic boom, or as we like to call it, the sonic thump. So phase 2 is about proving the accuracy of the predictive tools. And finally, phase 3, which is my focus at NASA and what I'll spend the rest of the time on, is about the conduct of community testing. We expect to overfly 4 to 6 communities in the nation to gather response data to the sonic thump, and ultimately deliver these data to noise regulators. And I'll identify who the regulators are in the next slide here. Of course, regulatory authority in the United States belongs to the FAA. And I'll point to Section 181 of the FAA Reauthorization Act, which exhorts the administrator to exercise leadership in the development of standards as they relate to prospective supersonic flights, and to work with national and international stakeholders as well. A natural place for that to take place is in the Committee on Aviation and Environmental Protection, a special committee within the International Civil Aviation Organization, and specifically within some of the noise working groups in CAPE. FAA is the US representative to that committee, and NASA is serving in the role of a technical advisor to the FAA in that capacity. I do want to emphasize once again, though, the purpose of our mission is really going to be to collect a body of data that can inform the standards that will be discussed and agreed upon by the FAA and the regulatory bodies at CAPE. So let's go ahead and meet the noise source. We're excited about the X-59 demonstrator aircraft and some of the properties that it has. It's been developed to have an acoustic signature and energetic characteristics like prospective future commercial supersonic transports. Here you see noise levels on a perceived level metric scale in decibels. And we can compare that to some other known phenomenon to get a sense of what kind of reduction in noise future transports might have. Compared to the Concorde, which had a 105 decibel perceived level noise, the X-59 is designed to deliver doses, noise levels around 75 decibels and some variation in that range. But you can see compared to a thunderclap or a car door slam inside the car, which could be very startling, the X-59 may have properties that are a little more tolerable, a little less startling to communities as it flies overhead. Related to the scope of the Quest mission, I want to be very clear about what we think we will produce, and no less importantly, what's out of scope for the mission. Our intentions here are to produce nationally representative dose response curves. You see kind of a cartoon of what that might be on the right-hand side here. And in particular, we're interested in two phenomenon. The annoyance that is a result of any single flyover, as well as the cumulative behavior. How do people respond to multiple flights per day? Additionally, we'll ask survey questions that will help us capture some of the effects of other things that might attenuate or increase annoyance. In particular, we'll be asking about the presence or absence of rattle, vibration, or startle that the survey participant experienced, as well as gather some information about their listening environment. Were you at home, at work? Were you indoors or outdoors? Were your windows open when you were indoors? And we'll be able to vary doses within the waking hours of the day in particular. So we will be able to have at least a little bit of variation with respect to time of day. But I do want to highlight that a few things are out of scope for the mission. In particular, we won't be assessing the effects of sleep disturbance. We won't be conducting overnight flights. In part, this is a safety consideration with our one and only X-59 aircraft. Also, we won't be focusing on gathering data for takeoff and landing noise, and we won't be focusing specifically on high altitude emissions with the Quest mission. However, I will highlight that other parts of NASA are actively researching these things and supporting research in these areas. If you look to the top figure there, you see an example of what we call the poster or the potential sonic thump exposure region. And you get some idea of what a notional flight path might be. The gray arrow indicating the straight line supersonic cruise, and the blue return arrow indicating kind of a subsonic loiter if the X-59 makes an additional pass over the area. See distinct regions for acceleration onto condition and deceleration, and really right there in the middle is where we believe we'll be able to effectively measure or estimate the resulting sonic thump. And it's going to be in that area that we draw our sample for this study. NASA intends to conduct 4 to 6 community overflights starting in 2025 and operating through 2027. I can announce that the first airfield has been chosen. Specifically, that's going to be in the vicinity of NASA Armstrong and Edwards Air Force Base, the purple dot you see in Southern California. And future airfields are to be determined. The community to be tested will be somewhere within a 100-mile radius of the chosen airfield. And we have some pretty extraordinary constraints that dictate where we could conceivably conduct these community overflights. The X-59 is an experimental aircraft. We have to have adequate runway and infrastructure, as well as backup airfields in the case of emergency landing. This is also part of the discussion surrounding representativeness of the data that we are to collect. And namely, my colleague Will Dobler has a paper indicating that some geographic variation could change the perceptual experience, that on average, the mean dose will be higher in the northern climates, and the mean dose will be smaller in southern climates, but subject to more variability. Likewise, we're dealing with the communities present at these test sites. And so judicious choice of test site also goes some way into building in the demographic diversity that we want in a nationally representative data set. Nobody blink here for a second. And so you can see kind of how a survey might unfold here. We'll be conducting multiple repeated surveys, including single event and end of day attitudinal surveys. And we have a near real-time need for data collection as we're trying to conduct upwards of 100 passes over the course of a month. So we'll be using internet and smartphone survey apps to deploy our surveys. Just to be very clear, the population under study will be all residents in that rectangular recruitment region. And you can see some of our intentions about how we'll go about collecting a sample. Right now, a notional sample of about 1,000 to be collected in each community. But we start from a sorted list of households, taking every nth household, and then randomly selecting a qualified participant within the household to get the study participant. In brief here, I'll summarize some of the activity around our noise exposure and design and estimation and analysis. And so first of all, we've come to understand more about the ranges that we anticipate producing with the X-59. Our nominal doses should range between 70 and 87 decibels on the PL scale. A optimization tool has been developed to help us optimize the noise exposure scale. And we've developed a sense of the meteorological data that we also need as inputs into our physical models for noise. A bespoke system of ground recording instruments is being developed. You see kind of the notional diagram up there on top. And we have a strategy for combining predicted noise models with actual measured estimates. Going to be deploying, something like 100 recording units across that large testing area. And so the combination of prediction with measurement will become our dose estimate. I'm nearing the end of my time here, so I just want to highlight what we think we might see based on some early testing that was done in the vicinity of Galveston. This was done using an F-18 aircraft and a special dive maneuver that kind of simulates the phenomenon of a quiet sonic boom. In particular, the data came 5,000 records from 371 unique survey participants. And you can see that annoyance was a fairly rare event, even among a group of participants who agreed to take your survey. They know you're doing this testing. In fact, 56% of those cases, they indicated that they couldn't hear the event in question. More detail are available in the contractor reports, as well as one of the academic papers by Lee. And it's been a long time in the making getting to the Quest mission. And in fact, one of the earliest risk reduction studies was done in 2011 in the vicinity of Edwards Air Force Base, again, using the F-18 aircraft. And so here you see two dose response curves from two different communities using the same aircraft and using the same maneuvers. And you can find more details in the contract report and again in Jasmine Lee's 2020 paper. I'll just highlight that at the highest ends of the QSF-18 dose range, there's about a 2 percentage point difference in annoyance. So while they are similar, they're not exactly the same. And so just by way of analogy here, we've seen the FAA neighborhood environmental study and the combination of results from 20 different airport neighborhoods to produce one national dose response curve. And so this will be similar to our objectives with the Quest mission and the community testing to combine data from 4 to 6 different communities and produce a nationally representative dose response curve. I'll highlight that the noise metric in question is different. We'll be considering impulse noise rather than the cumulative metric here. But the fact remains that we'll be seeking ways to combine data from multiple communities that we overfly. And just to conclude, I've given you a whirlwind tour of the Quest mission and its intentions to conduct community overflights with the X-59 aircraft. We expect the first flight later this year, and we'll begin the community testing in earnest in 2025. And the fundamental research question that we're trying to ask is, should that speed limit on supersonic flight over land be replaced with a noise-based limit, and at what limits? Thank you.
Thanks, Nathan. For our next presenter, we're going to continue on the supersonics, but talk a commercial supersonic operator. Dr. Akshay Oshak is sustainability and regulatory specialist at Boom Supersonic, where he aims to advance Boom's mission of sustainable supersonic travel by increasing understanding the impact of supersonics on the environment and then building solutions to mitigate those impacts. Topics of active investigation include sustainable aviation fuels, aircraft engine design and performance characteristics, modeling of climate impacts and environmental standard setting. Akshay leverages skills and experiences gained from his previous work as an environmental consultant at Ramble and during his graduate research work on aerospace and the environment to make sustainable supersonic travel a reality. Dr. Oshak has earned his master's and PhD degrees in aeronautics from MIT and his undergraduate degree in aeronautics from Purdue University. And I'd remind people, if you have questions, to go through the Slido app to ask questions for the presenters at the end of their presentation. So, Dr. Akshay.
Super. Thank you, Tim. And just want to say it's been a pleasure, being able to participate in the ANES this year. Thanks for having us over and giving me the opportunity to share a little bit with you about my company, Boom Supersonic, and kind of focusing on ways that, we're really looking at impacts to the environment, both, full flight as well as really honing in on local impact. So the talk here, the talk here is kind of two segments, if you will. The first is just a little bit more of an introduction about Boom Supersonic and the product that we're developing. And then I wanted to share a little bit with you about our efforts to mitigate local noise impacts, so LTO impacts around the airport community. So those will be the two focus areas. I'll touch on the other sustainability efforts that we as a company are bringing forth in this vehicle design. But certainly, if there are other specific questions on other areas, we can kind of talk offline, as it were. So advancing this, I want to begin kind of, with the thesis for the company, right? So, air travel, connects the world, links economies, enables people to kind of experience new cultures. And as you can see, intercontinental travel really has progressed over the decades. So if you kind of, look at the chart on the right here, it kind of shows the evolution between, 19th century steamship travel across the ocean, progressing to propeller and piston engine aircraft, and then the subsonic aircraft developed in the 1960s and then on. And what you'll note is there's really approximately a doubling of speed with each new technological generation. And so at Boom, we see kind of new possibilities by making further advancements into the speed of travel. So definitely increase productivity in terms of business trips, unlocking cities that were, maybe a once in 3 year, once in 4 year destination can now become more accessible. And I think fundamentally we believe that life happens in person, and so long distance relationships are facilitated. Certainly have a lot of other medical related benefits, geopolitical benefits, so on and so forth. And so Overture is the kind of main product or the product that Boom is developing. It's the world's fastest airliner. And I think the kind of top tagline there is something that I'm really kind of proud about and passionate about, both both myself and others in the company. So it's optimized for speed, safety, and you'll note sustainability, which I think is kind of baked into the very core of how we operate as a company. So a little bit of facts about the aircraft that we're developing. It's a Mach 1.7 aircraft. It's roughly twice the speed of current commercial transport aircraft. A capability of carrying 65 to 80 passengers, 4,250 nautical miles. And a little bit about the the other aspect of sustainability here, which is on climate impacts. We are designing both the aircraft and the engine, so the entire system, to be able to run on 100% SAF. And you can see there are some of the design features here that kind of take leverage advancements in vehicle design and development capabilities that have been unlocked over the years for us to be able to increase the efficiency of the aircraft. Introduce you to Symphony, which is our engine program for Overture. Again, efficiency, sustainability is kind of key drivers here. The focus is kind of making it affordable for operators to operate the aircraft, but then also you'll see here, a very, very strong focus on the noise impact. So things like, single stage fan up front to minimize fan noise, enabling kind of ability to operate on 100% SAF is a key one. You'll note there are no afterburners here. So that's, I think, a very big design choice that we've consciously built in to be able to mitigate local airport noise impacts. The vehicle itself, including the engine, but also more broadly, is being designed to meet the most latest current noise levels. So what's currently regulated for subsonic aircraft is ICAO Chapter 14 or FAA Stage 5 noise levels. For supersonics, we kind of see that we don't want to regress to kind of the existing regulations, as it were, which mandate much older levels. So we want to kind of start out by at least meeting what's the state of the art as of today. And so from here, I'll, hoping to share a little bit more about our design philosophy and ways that we are designing Overture to be able to meet these LTO noise levels. So, like I said, we are committed to ensuring that the aircraft and engine combination achieves Chapter 14 levels. We do have a little bit of a unique challenge here, though. So, traditionally for subsonic aircraft development, specifically looking at the engines, one of the more direct ways to reduce LTO noise is to increase the bypass ratio. So derive more of the thrust from the fan rather than the core of the engine. As you can see on the picture here, though, supersonic flight has, the physics are fundamentally different. And there is this aspect called wave drag, which, are all, so the drag caused by all of these shock waves that you kind of see depicted on this picture. And that scales as a function of cross-sectional area. So what you might imagine now is we have, for efficiency of the aircraft, we have a constraint on how big the engines can actually be made. And so that then means that for the, as a design constraint, we are kind of looking at medium bypass ratio engines. The flip side of that is relative to current technology and the way that aircraft are currently operated, those engines, because you're deriving more of the thrust from the core, you have a higher core velocity and therefore a higher jet noise from the engine. And so I mentioned before, we are targeting Chapter 14 levels. And so there have been a number of innovations that we've had to implement, we've had to pioneer for us to be able to achieve that. And so that, is kind of what I'll share with you on the next chart. So 3 buckets here, engine cycle, advanced procedures, and, design of the aircraft and engine. So when we talk about the engine cycle, I mentioned the kind of jet noise is one of the big drivers. A design constraint for us is to ensure that the exhaust Mach or the exhaust jet velocity has a cap to it, and to make sure that that's subsonic, so that we eliminate a lot of the supersonic shock cell noise just from the jet, right? And so, typically what you might think of for supersonic engines is you have, this long tail that you can see. Symphony is designed not to have that, so it's a non-afterburning engine as well. I'll get to the advanced procedures in just a bit, but just to touch on the third point, I mean, it kind of goes through to some of the design characteristics that are baked into the aircraft and engine. So we're really doing a lot of work to evaluate different, nozzle and inlet configurations to be able to minimize, some of the kind of tonal frequencies and such. And then I think the key thing here is our use of what's called the variable noise reduction system, or VNRS. And you see on the chart that's depicted below a notional takeoff trajectory profile for Overture. And so, at its short, what this really is an automated system that both commands thrust reduction as well as aircraft configuration changes. So changes in the flap settings and things like that during the takeoff procedure. And so this is something that we're pioneering. It's been able to, both minimize, LTO noise, both from a certification perspective, but then, in order to achieve the Chapter 14 levels. But then also, we are kind of looking at tuning that, optimizing it for different population exposure maps as well. And of course, we are at the design development stage of the aircraft. I forgot to mention this previously, but our first flight is anticipated to be in 2027 with certification by the end of the decade. And so at this stage of aircraft development, we have a whole bunch of models, a whole bunch of software that's used to calculate both the aircraft performance as well as the aeroacoustics. And so those would really, have to be validated against something in order for us to have confidence that, the aircraft is doing what we expect it to do, and B, to increase confidence in the validity of our simulation. And so, you'll see some examples here of our in-house computational aeroacoustics models. But then also, very importantly, we have undertaken a number of wind tunnel tests and plan to do so in the future in order to kind of, again, close the loop in terms of validating, designs and what our models predict the impacts to be. And finally, just a quick note on our, overflight or, sonic boom impact. So our business case, Overture's business case, is really looking at transoceanic routes. And so from our calculations, we kind of see that the market is ripe for more than 600 routes that are viable for supersonic transport. And so what we are very kind of mindful of, and again, it's one of those things that's baked in right from the start, is to respect, Dr. Cruz mentioned, the overland speed limit, and notably, eliminating sonic boom impacts to communities over land. And so, there's a good amount of effort within the company to develop fleet planning and route optimization tools, which, of course, objective is to get from point A to B, but to do so in a way that minimizes the amount of fuel that's required, but also ensuring that sonic boom impacts both primary boom as well as things that are reflected off of the atmosphere do not impact land masses at all. And so, just to wrap up, I mean, if I wanted to really get the message across that, even though Overture is still in the design development stage at this point, sustainability is kind of a key thread that runs through the company. And so noise is one of the most critical design drivers that, go into the decisions that we make for designing the aircraft. And so the goal is to be able to achieve Chapter 14 noise levels through these innovations that I've just covered. One of the key things that we hope that the contribution is not just for Overture, but also more broadly, is that there appears to be a good viability for some of these technologies to then also be potentially applied to subsonic aircraft. And then finally, as I just mentioned, the sonic boom impact is something that we are very firm about, that not having any impacts on the land or to land masses. So that concludes it. Thank you for your time and allowing me to share a little bit with you guys. Thank you.
Thank you so much, Ashke. We're going to transition now, and we have one virtual presenter with us. Well, not with us, but he's virtually here. So we're going to get him up on the screen here, and that is Joseph Oldham. He is the president and CEO of New Vision Aviation. He is a native of the San Joaquin Valley, and he's been a private pilot since 1974. He's had a passion for aviation since early childhood. A graduate of California State University, Fresno, Mr. Oldham has spent most of his professional life working to improve air quality in the region through deployment of clean energy and clean vehicle technology. Mr. Oldham is president and CEO of New Vision Aviation. It's a 501(c) nonprofit charitable organization, and it's focused on providing aviation education for youth and residents of communities of color and low-income neighborhoods in the San Joaquin Valley. Mr. Oldham is the lead pilot and project manager for the Sustainable Aviation Project, designed to validate operations of electric aircraft, and has over 230 hours of flights in the Pipistrel Alpha Aero electro aircraft. This is the first production electric aircraft in the world. The project is beginning the process of getting the public familiar and comfortable with electrical propulsion in aircraft as a step towards the advanced electrical powered aircraft or aerial sky taxi vehicles of the future and larger commercial electrically powered aircraft. Mr. Oldham is a contributor to the NASA white paper published in 2021 on the potential for regional air mobility using advanced electric aircraft to change how underutilized regional airports can bring enhanced mobilities to the communities they serve. Please help me welcome Joseph.
Thank you. Appreciate it. I enjoy, I wish I could be there with everybody today, but unfortunately, challenges with my schedule have prevented me from getting up there. So if I can get this thing to show the full, oh well, I'm not going to bother. So in 2018, we received 4 Pipistrel Alpha Electros. And it was part of a project that we had designed, developed basically to show the viability of electric propulsion in aircraft. The San Joaquin Valley has a rich history of aviation. It was a main training area for pilots prior to and during World War II. We have a lot of general aviation airports in the valley, basically about 32 of them between Sacramento and Bakersfield. And the weather here is almost ideal for flight training. So the goal of this project was really to see what electric aircraft could do in terms of lowering cost for, as was mentioned, our primary focus is working with youth from our communities of color, which have been really excluded to large degree from the aviation industry, from getting into high-paying aviation jobs because of the cost barrier. And so we know that training aircraft, Cessnas, Pipers, whatever training aircraft you kind of choose, are pretty expensive to operate. And so the cost for flight training has steadily risen. So the idea bit was basically, okay, let's see what these electric aircraft, because we know based on deployment of electric vehicles in general, electric cars, buses, etc., that electric propulsion has a huge cost savings in terms of cost of operation and maintenance costs. So we wrote a grant, and we were successful at getting funding to the tune of about $1 million, which allowed us to acquire 4 pipistrel alpha electrodes. We took delivery of them in March of 2018, and we started the process of testing and validating these aircraft and seeing how they would integrate into an existing flight training operation. Now, we ran into one major barrier with pipistrel aircraft was the way the regulations are written around electric propulsion for aircraft that are classified as light sport. Light sport aircraft is defined as having a single reciprocating engine if powered. An electric motor obviously is not a reciprocating engine. So we set about working with the FAA to put forth a petition for exemption to allow us to use these aircraft for flight training operations. And it's taken about 4 to 5 years now for them to finally kind of get around to working on that petition. But in the meantime, we had a lot of testing to do and a lot of validation work to do, which we would have done anyway, because this is all new technology. So we started flight operations basically in 2018. Initially, we were doing a testing program to acquire data for the FAA to help support our petition for exemption. We set up charging infrastructure at 3 airports, Mendota Airport off to the west, Fresno Chandler, which is, you see, kind of the center of these operations, and then over in Reedley's Airport off to the east. And all of these airports were within range of the Alpha Electro with a full charge. And so we've operated these aircraft now to all of these airports and even beyond. Back in 2021, I took an Alpha Electro and I flew it from Fresno to Lodi near Sacramento, kind of hopscotching up the valley, doing about 35 nautical mile trips at a time, and charging the aircraft up using solar powered electric car chargers, which were portable, and we could actually move them along. The Beam Corporation provided those at no cost to us, and it was an attempt to show how you can actually fly electric airplanes using solar power to recharge them. And it was very successful. We covered about almost 230 nautical miles. So as I said, we got the aircraft in March of 2018. I personally have accumulated over 220 hours of flight time in them. We've traveled well over 3,000 nautical miles with the aircraft. The aircraft have been flown by a variety of folks in the aviation industry, professional airline pilots. The FAA actually sent a test pilot out to fly with me for 3 days in the aircraft. They've been evaluated by engineers from the FAA and many aircraft companies that have been developing advanced electric aircraft have actually come and visited and sent some of their people to fly with us in the aircraft. And we were doing this as all part of our test program for the FAA and for our petition. In that cross-country flight in 2021, using the solar power, I covered about almost 228 nautical miles, used about 66.4 kilowatt hours of power, and our fuel economy was about 3.43 nautical miles per kilowatt hour. And that was at a very economical speed of about 60 knots. The aircraft has a really broad range of flight operations. It can fly as slow. I think it stalls at something like 43 knots and can cruise it up to 108 knots. So it has a big range of operation. And we found that the most economical speed for it was its best L over D speed at about 64 knots. So some of the community benefits that we have observed and have been, kind of obvious from having the aircraft, you have no engine run up. There is a run up area, of course, at most airports for aircraft, the piston engine aircraft. Typically you go to the run up area, you run the engine up to, about half power. You check the mags to make sure that they're working properly. And all of this creates noise. And of course, burns fuel and in many cases wastes time for the students that are using the aircraft. In the Alpha Electro, you don't do any of that because you have no mags. You don't have to wait for any oil to get warm. None of the typical things that you have to do with a piston engine airplane. One of the most disconcerting things for pilots is when they first get in the aircraft and you start it up, the prop doesn't move. But then when you go and stop, the prop stops, and they're not used to seeing that. And that's actually kind of funny when I've taken people with me, and that's one of their most common reactions, like, "Oh my gosh, the prop stopped. Oh my gosh, it's quiet. We can actually talk in this thing. That's amazing." Observers on the ground have noted that the aircraft are absolutely silent at 1,000 feet above ground level. And that's really cool for the community. Fresno Chandler Airport is actually surrounded on about 3 sides by residential neighborhoods. And the people in this community for decades have expressed their concerns with the noise that this airport produces. And as you may be aware, that's a common problem now, is residential neighborhoods are beginning to encroach what used to be airports that were actually out in the country. Reed Hillview is a prime example of that, as well as Santa Monica Airport down in Los Angeles, and a number of them. And that's a threat to the continued survival of these airports. Electric aircraft actually can be a great way to eliminate or significantly mitigate that noise nuisance for the community around those airports. We did some noise testing for the Electros as part of our petition for exemption. We recorded a 71 decibel reading during full power takeoff, measured about 275 feet from the runway center line. We compared this to typical training aircraft that were also operating that day, Cessna 172s, Piper Cherokees. They all recorded a decibel reading of about 80 decibels. We even had a few King Airs that were taking off, and they were recording a reading of over 90 decibels. So significantly less noise from the electric aircraft on takeoff. And the primary source of that noise is the propeller. As the propeller obviously spins, it produces a noise signature as it cuts through the air, and that's where you get most of the noise. The actual electric motor just makes a kind of a whirring sound. From the ground, most of the time, people have noted they sound like very, very quiet little turbines taking off. So the crew benefits, noise levels in the cabin are low enough that you can actually remove your headset and talk without having to yell or scream at each other, which is really cool. They are very smooth, and flight inside of an electric airplane is extremely relaxing. I had to do 100 hours of endurance testing on one of these aircraft, and did a lot of flights, back-to-back flights over a period of a few months. And oftentimes it would get so relaxing up there that I'd kind of like, oh my gosh, I might fall asleep up here. This is not good. So they are a very relaxing environment to be in for the crew. Some of the potential risks, though, are if people around airports are used to hearing engines and used to hearing aircraft as they move. Because the Electros or electric aircraft do not produce any initial noise at startup, it can be a hazard to people that want to walk up to the airplane, maybe not thinking that either the aircraft is occupied or that the aircraft is getting ready to start. The Alpha Electro actually has a special switch for the prop, for the throttle. You can't, if you activate the throttle switch and the throttle is actually moved off of its zero position, the prop will not turn. You actually have to move the throttle back to the shutdown detent and then move it ahead for the prop to actually turn. We set up some procedures where we basically turn all of the lighting on before we start the aircraft, and then of course we announce that we're about to start, clear prop before you start to move, and that seems to have been working out just fine. People on the ramp areas, however, may not hear you as the plane is even taxiing. They are that quiet. And so the pilot needs to be very aware that the aircraft is very quiet and take appropriate precautions. If you see somebody walking or moving that might not understand that the aircraft is there, then you basically want to just shut it down and let it coast and make them, be as cautious as you possibly can with people out on the ramp area. So with that, if there's any questions, I'll answer those later on. This is an image taken as we were coming into land at Modesto. Many of our valley airports are surrounded by residential communities, and so electric aircraft are going to be a big benefit for operations in the San Joaquin Valley. And so as well as I think they will be in many, many, many parts of the rest of the country. So thank you very much. And I really appreciate the opportunity to share what we've learned from actually having these aircraft for about 5 years.
Great. Thank you, Joseph. It was great to have a GA perspective on our panel. And I would like to introduce our final speaker and the final speaker of the conference, the coveted spot that Ben Goldman has. He's the manager of acoustics at Archer. Ben began his career with Bell Helicopter, where he spent 5 years improving their acoustical prediction methods, as well as learning field test and civil certification procedures. Prior to joining Archer, Ben spent 2 years at Joby Aviation, leading the aeroacoustic design of their vehicle. His current responsibilities include leading design of the cabin and external noise profiles for Archer's production vehicle, Midnight. Ben holds a bachelor's degree in aerospace engineering from Purdue University and a master's degree in aerospace engineering with a focus on aeroacoustics from the Pennsylvania State University, where he studied under Kenneth Brentner. Please help me welcome Ben Goldman.
Afternoon, everyone. Thank you for inviting me. Thank you for your focus on this last most exciting presentation. Just status check. How many people in the room have heard of Archer Aviation? Wow, that's awesome. I'm surprised. All right, great. So today I will be talking about designing urban air mobility for low noise. Let's get started. So who we are, like I said, I was a little surprised you guys know who we are, but for those of you who don't, we have now designed and we are manufacturing a safe, sustainable, low noise, all electric vertical takeoff and landing aircraft with the goal of being first to market in 2025. There's a lot of adjectives in that statement. The big one to start with is the all electric vertical takeoff and landing. So we shorten that to eVTOL. And so I'll use that term probably a couple of times through the rest of the talk, but that's the one to familiarize yourself with. I'll cover the rest of them as we go. All right, so the first part, the eVTOL, electric. It is the advancement of electrification that has enabled this technology first and foremost. We have seen tremendous growth in the specific energy density of batteries over the last 30, 40 years. In particular, in the last few years alone, we have reached a so-called magic number of about 250 kilowatt hours per kilogram, which basically enables this technology to be a viable business model. The other way to consider that, though, is that we have only just reached the point of market viability. So we are at a razor's edge of having a product that will actually make a profit. So we need to be keenly focused on actually making a product that is efficient, that will allow us to make money and profit as a business. So a little overview, Archer UAM, this is the urban air mobility concept as we are building it out. We plan to move people less than 100 miles within and around city centers. The early launch markets, you may have heard a couple of the announcements thus far, New York, Chicago, LA, Miami, largely congested areas that are dealing with high throughput and need solutions for these high congestion areas. The early launch routes will be these trunk routes. So basically the main routes that go from airport to city center. There's already an existing demand and a willingness to pay. I can add to that there is also to some extent, an acceptance of the noise as a status quo. So there won't necessarily be such a strong pushback to introduce this vehicle. Let's see. So the first phase is expected to rely on existing and retrofitted infrastructure. And we then plan to expand out based on aligning with development partners to build higher throughput vertiports. So the aircraft that we have designed as an overview, I mentioned it is electric, it is vertical takeoff and landing. In terms of performance, we are planning a range of up to 100 miles, but it is optimized specifically for 20 to 50 mile rapid back-to-back trips with minimal charge time. Speeds of up to about 150 miles an hour and payloads of about 1,000 pounds. So a 1+4 pilot plus 4 passengers with room for golf bags. The advantages. Safety first and foremost, that's our primary concern. The vehicle as a whole will be certified at levels similar to today's commercial airliners, but distinct from helicopters, there are no single points of failure. So the distributed electric propulsion systems that we are using, having multiple propulsors on the vehicle means that any one of them failing doesn't mean the vehicle is coming down. In terms of noise, we are stating about 100 times quieter than a helicopter on average. We are not yet ready to put precise numbers to that, but on order, we are about 20 dB quieter than a helicopter. More so up on wing, we're quite a bit quieter than a helicopter by 20 dB. And in terms of cost, we are about 1/3 of the cost to manufacture and operate relative to a helicopter. All right, so let's get into some of the design of the vehicle itself. So there's a whole slew of factors that go into the design of the vehicle. Any one division, any one group is going to say that theirs is important, but it's a huge design space. And so where do you get started? What I alluded to in one of the first slides was the electrification enabling this technology. But as I said, it has also only just enabled this technology. So the really limiting thing, the thing that we need to focus on first is the performance, because that's the only thing that if it fails means that we will not have a viable product. So let's ask ourselves this question. Which one is more efficient, thrust-borne or wing-borne flight? I don't know why there was a second image that came up. It's too bad. It's supposed to be a little helicopter right here. All right. Well, anyway, let's imagine there's a helicopter under that first equation. The idea is basically it's an inverse relation between the two concepts. One has a large acceleration of a relatively small amount of air. In the case of a wing-borne flight, you have a small acceleration for a large mass of air. Oh, there it is. All right. So starting from ideal power for hover, so just imagining that we are looking at some system that is going to be thrust-borne. When we write out the equation for ideal power, we can see that there is a term for area in the denominator. What that means is that the larger the area of the rotor, the lower the ideal power. So you can just imagine you have more useful area with which to displace the air. So that kind of that implies the fall off in this curve. It's a 1/n, as you can see along the x-axis, such that as you decrease the area of the individual propellers, the power required goes up, and therefore the efficiency goes down. That makes sense if you think about the area term itself, because really what you're doing is swapping an exponential, right, like a r² for just a linear n term. So in general, the total area of the propellers will go down as you move away from a single propeller. So in that sense, helicopters are the optimal solution for hover. That's why they were built. That's why they were designed that way. They're great at what they do. In terms of a vehicle as we are designing it, that performance is going to sit somewhere in this tilt rotor section right here. So not quite at the capability of a helicopter, but still pretty good and still much better than the direct lift or lift fan concepts. Now, when we look at cruise power, so wing-borne, We can write out this equation in terms of a lift over drag term that again is in the denominator, which just says that when the cruise efficiency is higher, the power goes down. That should make pretty good sense. And here we see that sort of the fall off of a helicopter, right? The cruise power of a helicopter is very high because it has a poor lift to drag ratio. Conversely, something like a glider, which is just intended to stay up and cruise for a long period of time, has a very low power requirement because of a high cruise performance efficiency. So the vehicle we are designing will cut kind of in the middle of that. We will have a higher performance ratio than that of a helicopter and a lower performance than that of a glider. What that means in the summary is that we are taking the best of both worlds, right? We have hover performance that is nearly as good as a helicopter. We have cruise performance that is better than a helicopter, matching that of most wing-borne systems. And we should note that the majority of the time the vehicle is operating is wing-borne, right? We're only considering these vertical maneuvers for a very short period of the mission. So it would behoove us to use a lower cruise power. So that's why we have a wing-borne concept. Now let's look at the blades. The aerodynamic models, the design tools that we used are pretty traditional. You start from geometric constraints, you consider operational constraints. These things help to reduce the design space to understand what you can really actually affect and what you can really consider as options. What we've done uniquely is actually simply add noise minimization to our targets. So we are simply looking at aerodynamic designs that also help to reduce the noise and meet our performance requirements. In terms of design tools, our aero and acoustics teams have built a modular framework to support these multidisciplinary predictions. So we've grouped together our CAD for design, structural sizing, CFD, and noise all together. This allows us to create a product that is truly fully optimized for the mission. All right, now a little bit of detail on the propellers. So Midnight is somewhat unique, aside from being a eVTOL aircraft, in that we have two types of propellers. We have a simply called a tilter, which tilts from a vertical takeoff and landing profile to a cruise position. We also have a lifter, which simply acts to lift the vehicle off the ground and then stows. So in that case, the tilter has variable RPM since it'll be used through multiple phases of flight. In that same way, it'll have variable pitch to allow for, like I said, takeoff and cruise conditions. And it is a relatively complex propeller. The lifter, on the other hand, which is just intended to support us for vertical takeoff and landing, does also have variable RPM, but it is just fixed pitch. Will stop in cruise and stow at a low drag configuration, and is quite simple. Acoustic considerations that went into these propellers, particularly on the tilter. So low tip speeds, that is absolutely critical. That's the first order effect. That's what gets the overall noise levels down. But then we also need to consider the advance ratios, the transitions, and the edgewise flight. So we also need to account for low advance ratios in transition and cruise. What this does is prevent the onset of this typical wop-wop sound that you hear from a periodic change in the loading as you get edgewise flight typical of a rotor. So we have a low advance ratio, which means you get a very minimal wop-wop effect. And as we move on to onto wing-borne flight, there is no edgewise cruise at all. We are now simply a propeller that has a nice clean inflow of air, much lower noise. We have focused on minimizing the boom and wing interactions. There have been a number of studies that NASA has generated that show that there are loading effects that come in when you start mixing the inflow between a boom and a blade or a wing that's interacting with it. We're minimizing self noise, right? So the noise that's generated by ingestion of the wake generated by this propeller or a neighboring propeller. And most uniquely, I would say, is our ability to now balance the tonal and the broadband components of the spectrum. When you're starting from a rotorcraft, the tonal component is absolutely dominant, right? You're at such a high tip speed that there is nothing about the broadband noise that you can really affect. It's really the tonal aspect that dominates the whole character of the noise. When we bring the tip speeds down as low as we have, below 0.5, now we are able to actually play around with how tonal, how broadband is the acoustic signature of this propeller. In terms of the lifters, similar layout. So again, low tip speeds in hover, low advance ratios in transition. We are focusing to minimize the interaction between the tilter and the lifter. Of course, the lifter through transition will ingest a bit of the noise, ingest a bit of the wake that's being produced by the tilter. So we've made efforts to minimize that interaction, again, minimize the interaction with its own boom, and additionally balance the tonal and broadband components of the signal. So what I've talked about is ways that we can minimize the noise of the propellers, minimize the noise of the vehicle. And the next step, of course, layers of the onion, is ways to minimize the community noise. So we, as a first order, reduce the impact by optimizing these trajectories. So we take the very same framework that we have in terms of aeroacoustics, our aerodynamics and acoustic tool chain. We wrap into that our Volpe advanced acoustic module, which allows us to generate noise contours on the ground. This can then be utilized for multiple purposes. We have a operations and business case simulation framework that allows us to design our business models, understand what markets we want to go into, how we design the routes, how we plan the business case. And then we also have a optimization loop that we can now add, because once we have these contours, once we know the contour areas, we can then feed that back into our system, understand what trajectories are giving us the highest noise, lowest noise, and optimize thusly. At the bottom, you'll see just a couple example contours. These are actually real contours we've generated. I've stripped out all the useful information, so they don't mean anything, but it does imply the significant change in areas that we are seeing from this optimization. And lastly, noise abatement still applies. I don't mean to dig on Teslas. It was just a easy access, but in general, electric cars are very quiet. But when you drive them aggressively, in the case of plaid mode, which is like my favorite thing with Teslas, they're much louder, right? So there's no idiot-proof solution. You can design something to be quiet, and then you can still operate it in a loud manner. So it is still very important for us, both as designers of the vehicle and those responsible to train the pilots, to understand that noise abatement is still an important part of the operation of the vehicle and how we interact with the public. So fly neighborly. And with that, I end with 26 seconds.
Thank you very much. I really appreciate all of this information. And I know we do have a hard stop because there is a TRACON tour going on after this. So we can start the Q&A portion, and we did get some great questions. The first one is I believe it's for Dr. Ashok. How noisy are the supersonic engines during taxi and takeoff? And will they be better or worse than stage 5 or lower engines? And so what are the effects to the communities close into an airport?
Thanks for the question. So I think two parts to this. Let me address the takeoff one first. So as I mentioned, one of our key design constraints is to achieve Chapter 14 or Stage 5 LTO noise levels. And so our design of Overture, that's absolutely one of the targets that we have to achieve, that we are setting for ourselves to achieve. For the taxi phase, I think one of the things about supersonic engines is they are designed, the kind of 100% thrust setting is actually designed for top of climb. That's when the energy, that's when you require the most amount of energy from the engine. And so at any other phase of flight, i.e. during taxi, for example, you are actually operating at a lower thrust percentage or throttle setting relative to other aircraft. So, that should, I think, help in terms of alleviating some of the taxi phase noise as well.
Great, thank you. And we have 2 questions here for Dr. Cruz. We're going to put these ones together. Is the X-Wing X-59 being developed for civilian or military use? And what altitude do you expect these flights to be conducted at, the test flights?
Start with the altitude question. I did have some supplemental slides that I didn't get to share. You can also check out the Quest mission website. But we expect to operate the X-59 at 55,000 feet with about a speed of about Mach 1.4. That's about 925 miles per hour. As far as the purpose for the development, it's for civil applications. The data we produce are to be consumed by the International Civil Aviation Organization committees, and you saw the word civil in the current prohibition over land. So we're really trying to form regulations surrounding the operation of civil aircraft.
Great, thank you. A question for Ben. Is the lifter restarted for landing? And if so, when and how is that done?
Yes, certainly restarted for landing. There is a sort of hysteresis loop concept similar to the way it's implemented for some of the variable reduction systems in helicopters, such that there is a range of RPMs over which the propeller will spin up and maintain its RPM. Yeah, as you're moving down in altitude, right? You're decreasing the airspeed of the vehicle. The propellers will come on and stay on as that airspeed goes down. If you were to then increase airspeed again past some threshold, the propellers would stop again.
Okay, thank you. This question is for Joseph, but he's still with us. What's the biggest obstacle in getting the electric pipistrel operating at other airports?
Well, the biggest obstacle is really infrastructure, electric charging infrastructure, which I think is going to be that's going to be an obstacle for all electric aircraft, no matter what size they are. Good news is we're starting to see movement within state governments and even the federal government about potentially providing some grant dollars to help mitigate some of the cost of putting that infrastructure in place. You know, California is working right now on a solicitation, I think, for some funding to do some projects jointly with the CEC and the California Resources Board. So that's a big plus. And Washington State's already been working on this for a while. So infrastructure aside, then we get into the regulatory things. You know, electric propulsion is accepted in Part 23 for Part 23 certification. And I know the FAA has been working on, obviously, certification of the eVTOLs and other an eCTOL aircraft. I believe that the FAA is going to probably speed up some of the regulatory or smoothing out some of the regulatory barriers. We still have a regulatory barrier for light sport aircraft, which are actually a really good early place for these aircraft to be actually implemented, because the aircraft are light. They don't have as much weight, so the battery weights can be low, you know, not as large, and they can be used quite well in pilot training.
Great, thank you. And while we have you, I want to ask a follow-up question, how much cheaper would it be to get your private pilot certificate in a pipistrel than just in a traditional 172?
Ooh, well, typical 172 cost, you know, in the typical scenarios these days is about $10,000 to $12,000 to get your pilot certificate for private pilot, assuming you get it in about 50 hours or so. And for a pipistrel Alpha Electro, it could be about a third of that easily. Could be cut. It could be cut down to about a third, or 2/3 of that cost could be eliminated. The Alpha Electro will operate for an hour on about $5 worth of electricity. A 172 burning 8 gallons an hour at $6.40 a gallon. Yeah, you can kind of do the math, right? And that's just for the fuel. And there's no oil to change. Yeah, there's no spark plugs to change. The electric propulsion just has a huge advantage from a cost savings perspective, which is, of course, why a lot of the you know, the eVTOLs are going to be amazing, and they're going to really help. You know, in terms of lowering cost of moving people short distances.
Great, thank you. This question is for Ben. Are you planning a San Francisco to San Jose route? And have you reached out to anyone in San Mateo or Santa Clara counties? And if you did this, would you be staying over the Bay the entire way?
Well, a couple parts to that. Yes, we are planning, certainly planning multiple routes within the Bay Area. I don't have the contact information for any of those the administrative contacts within the area, but I can put anybody that's interested in touch with our people who would know. And the last question was, the last portion of that was,
Let me see, I already cleared it. The last portion was, are you going to stay over the bay the entire time?
that was right, thank you. There is no direct plan to do that. We may leverage that as a means of ease of access into the market. But the plan is to not necessarily need to stay over those routes. The whole point is that we are trying to move into denser urban environments and not rely on these circuitous routes to minimize noise.
All right, this question is for Nathan. For people in your testing, for your testing area, are you going to be testing areas that have current aviation noise or areas that aren't exposed to aviation noise? And how would you define how people are exposed to noise?
Sure. There's definitely an intention to reach populations that are not routinely subjected to aviation noise. In terms of how one could distinguish those, would have to be based on some distance threshold from an airport, for example, and you could kind of overlap that with the recruitment region. And so those who are inside that airport ring may meet the definition of exposed to airport noise, whereas those outside would be identified as not routinely exposed. Part of the nuance in the demographic selection too, there's an intention to visit kind of a mix of urban and rural settings as well too. So we definitely want to expose broad swaths of the U.S. population to this new sonic thump that we're trying to measure, right, and gauge perceptions.
And for Akshay, how can communities be sure that the VNRS will be used during regular operations? Wouldn't the aircraft be louder if it were disabled, turned off?
Thanks, Tim. And yeah, thanks to whoever asked the question. I think that's a very pertinent question to what, to what is kind of inherently, required to be able to meet those noise levels. So it's a question that we've actually been asked even by, regulators and, even within ICAO, CAPE and things like that. So the VNRS is envisioned to be an integral part of the procedural processes within the takeoff cycle for Overture. And so, contrast with maybe some of the options that currently exist for subsonic aircraft, such as D-rates and things like that. This is kind of a little bit different in that it's part of the takeoff process, and it can only be kind of deactivated if absolutely needed under like safety circumstances, for example. So, that's kind of the way we envision to implement it. There's scope for, it's also likely not, there are kind of a minimum level of VNRS profiles that we need to achieve the noise levels, but then there is potentially some leeway there as well for even more stringent, kind of lower noise profiles if the aircraft is capable. So, for example, if it's not fully loaded and you have a long enough runway and things like that, then you can even, think about tuning it even further should the case arise.
I can expand on that. From a higher level, the FAA doesn't permit VNRS systems or anything that's called a VNRS system if there is the option to turn it off, right? So those systems are not things that the pilot would have the ability to turn off. Otherwise, you would assume the worst case scenario.
Barring the safety implication, of course.
Thank you. An additional question, Mr. Goldman, as routes get established, what type of outreach has Archer done to engage the communities or will do to engage the communities that will serve and fly over?
Great question. So just in the last few months, we invited the whole group of local community members to come out, witness our subscale maker vehicle flying and operating over the Salinas Airport. So that is a first order, just introducing them to the concept of what an eVTOL is. We are further planning engagement with the cities, and the cities that we've already publicly announced, so New York and Chicago, we are actively engaging grassroots campaigns to, in a similar thread, introduce those communities to the vehicle, introduce them to the concept and the operations that we are planning to operate.
I think we have time for a couple more questions. I believe this question is for Akshay. What metrics will you use to assess the noise impacts?
Sure. I mean, we are kind of using, or we are, following what's currently established in terms of noise metrics and measurement requirements. I mean, certainly within the LTO, there are, it's a lateral kind of sideline approach and downwind points that, as are required for current operations. So we kind of follow that for our impact measurement.
Thank you. Yeah, I think that answers. Question for Ben. Can you address low frequency noise and how you are designing to address low frequency noise in your aircraft as opposed to compared to helicopters?
Sure. So the reason why helicopters experience such intense low frequency noise is that they have typically a low blade count at a very high rate of rotation that introduces these relatively low frequency introductions of a blade passage, right? So what you're doing is you're not actually experiencing the noise specifically of the blade, but actually the passage of the blade. So it's getting louder as it passes the advancing side of the propeller disc. And so what you're hearing is this beating pattern. That is the low frequency content that is typically most disturbing. That's the thing that when a helicopter is coming at you at 100 knots, you can hear from a mile out. The whole reason that I was leaning on the concept of avoiding edgewise flight is exactly that. When you have no edgewise rotation of the blade, you don't get the loading oscillations that you would from a helicopter, and therefore what you instead get is a frequency drone that is just dependent on the rotation rate, but much more akin to a traditional fixed wing prop than the beat of a helicopter.
This is I guess, two-part question for Dr. Ashok. What do you expect the airfare to be for a flight from New York to London, for example? And how fuel efficient will supersonic flight be compared to commercial flights of the same size?
Thanks for the question. So on airfares, we are kind of targeting this to be comparable with current business class fares. That's the expectation for the first version of Overture anyway. I will make a note that, we are just an OEM or aircraft manufacturer. And so, ultimately airlines are the ones who will be setting those prices and, doing it with their own business case and things like that. But we do expect our aim is to make it kind of profitable, at the starting level, but then also continually improve that to widen it, make it more accessible. On the fuel efficiency side, I mean, that's a good question. So we've done a number of studies and for a comparable product relative to subsonics, we anticipate between 2 and 3 times the fuel burn. So it is absolutely right that there is increased energy requirement for supersonic flight in order to be able to achieve those time savings. What I will note though is if you look back historically, I mean we are kind of entering new entrants, as it were, and so I fully expect that there will be a continued scope to improve the design and improve the fuel efficiency performance. As designs get iterated as the technology matures, in a broad sense for supersonics.
Okay, thank you. And our final question, Ben, as the final speaker, you get the final question. When are you expecting to have first flights outside of the testing phase?
If we're speaking operationally, the intent is to start operating within the markets we have discussed with as early as 2025.
Great. Well, thank you so much to all of our panelists again. Really appreciate it. And I will turn this over to Sandra. If we have any, or Justin, if we have any final comments.